Collision is one of the most fundamental parts of any game, which is why I find it so strange most game developers deliberately avoid learning how it works. It's often assumed that game engines will perfectly take care of it all, but I think that's quite a strong assumption to make. That doesn't necessarily mean everyone should make their own game engine, but knowing the basics gives you a better understanding when things go wrong. In this video I'm going to explain collision systems, how to set a basic one up, and optimizations to improve performance, including Quadtrees. This video assumes you already know how to calculate a collision between two shapes, which is a topic I discussed in a previous video on separating axis theorem. I'll make sure to leave a link in the video description for those who want to learn more about that. Let's get into it. A collision system contains a number of objects and needs to work out which are colliding. The simplest approach to do this is to go through each object in the system. For a given object, you compare it against all other objects. So is A touching B, A touching C, A touching D? Is B touching A, B touching C, B touching D, and so on. This guarantees all collisions are found. However, this approach of looping through the objects for every object is not scalable. Every time you add a new object to the system, the amount of checks it has to do increases exponentially. We can show this with big O notation. The number of operations the system has to do, O, equals the number of objects in the system, N squared. So if you have 10 objects, the number of checks is 100, and 20 objects, the number of checks is 400. Plotting this on a graph really emphasises the number of checks the system has to do. If this is running for every frame of a game, it will eventually become overwhelming and slow everything down. Luckily, there are a number of ways to improve this. For example, splitting objects into active and static groups. Static objects don't change between frames, so once they've calculated their collisions, they don't have to do it again. This would mean the number of operations O is equal to the number of active objects A squared plus the number of static objects B times by the active objects. This can improve things greatly, depending on the split between active and static objects. However, big O notation doesn't care about the exact number. It's concerned with scalability. By factoring out the smaller variables, this simplifies to ON squared. This indicates it still scales exponentially, the same scalability as before. Another approach you can take is to split objects into layers. For example, a physics layer, a game logic layer, and a user interface layer. This lets each layer focus on a smaller subset of the objects. The number of operations this has to do, O, equals the number of layers, A, times by the number of objects in each layer, B squared. Again, this can improve things greatly, depending on the size of each layer, as you split the total number of objects into smaller subsets. However, factoring out the smaller variables still leaves you with a squared factor, which means each layer still scales exponentially. The next approach you can take is splitting the collision systems into areas. This requires each object to work out which area it is in first, and then run collision checks on all the objects in each area. This would mean the number of operations O is equal to the number of areas A, times by the number of objects B, plus the number of objects in each area C squared. Again, this can improve things greatly, depending on the location of the objects, but there is still an exponential factor in play. In fact, there are scenarios where this approach is worse than the basic system we started with, such as when all the objects are in one area, or there are objects on the boundaries between areas. This is where Quadtrees come in. A quadtree is a structure that stores data based on its location. It uses a very simple method to do this, which can be used recursively to create more complex structures. Let's start with a basic quadtree. If we add a single object to it, A, that object is stored in the tree. If queried, the quadtree returns the object, which can be used to check for direct collision. It gets a little more interesting when you add a second object, B. The quadtree doesn't want to store more than one object, so it splits itself into quarters or quads, storing each object in its own quad. This works by running a collision check for each object against the quads in the tree. So for A, that is the top right, and B, that is the bottom left. This quadtree can be queried in a similar manner. First by asking which quad does the query area cover, and then returning the object in that quad, which can be used to check for direct collision. The magic kicks in when this is used recursively. This is done by turning each quad in our quad tree into its own quad tree, creating layers of quad trees. We can see how this works when adding a third object, C, to a quad that already contains an object. Our first quad tree layer works out which quad C belongs to, in this case the bottom left. It then adds the object to the quad tree in that position. Our second quad tree layer now splits itself into quarters, just like the first one did, moving B into the bottom left and C into the top right. To query, our first quad tree layer works out which quad the query area covers, in this case the bottom left. It then queries the quad tree in that position. Our second quad tree layer works out which quad the query covers, and then returns the object in that quad, which is used to check for direct collision. Now we understand the basics, let's have a look at an edge case. Adding a fourth object, D, on the boundary between the quads. The first layer quad tree knows this object is in the top right. The second layer quad tree splits into quarters, placing A in the top right, but D covers multiple quads. As such, it's best to store D directly on the second layer quad tree, as it isn't fully encapsulated by any further quads. With this, when querying the top right, no matter which section of the second layer quad tree the area covers, it will always return D, which can be used to check for direct collision. Similarly, querying on a boundary. Again, our first layer quad tree knows the area the query covers, in this case the bottom left. So we query the second layer quad tree. Since this query area covers multiple quads, all the objects from each quad are returned, which can be used to check for direct collision. Hopefully you can start to see how simple quad tree rules create complex data structures, which can be queried to return objects quickly. Now let's use one to create a collision system. To do this, we go through every object in the system. For a given object, we query the quad tree to look for potential collisions. That returns a list of objects which can be used to check for direct collision. Then we add the object to the quad tree. Finally, once we've done this for all objects, we can clear the quad tree for the next frame. In a system like this, the number of operations the quad tree has to do, O, is equal to the number of operations n log n. This means a quad tree scales logarithmically, allowing the collision system to grow significantly larger than the basic approach we started with. Plus, there's nothing to say you can't use the improvements we previously discussed, such as splitting active and static objects and using layers for categorizing collision types. Now this is just scratching the surface when it comes to this topic. There are plenty more improvements you can make to systems like this, such as combining query and insert functions to create an optimized quersert function, adding a remove function to the quad tree so it doesn't have to be cleared every frame, and if you're interested in 3D, adding an extra dimension and exploring how Octtrees work. So to sum up, basic collision systems loop through their objects to guarantee everything is checked. However, this scales terribly. There are improvements you can do, such as static and active object splitting, logic layers, and collision areas. Quadtrees are a better way of implementing areas and improving the scalability of a collision system. They work by adding objects to their quarters, and if there's already an object in that quarter, recursively splitting until the object belongs to its own quarter. This can then be queried in a collision system to return potential collisions. I hope this explanation was easy to follow along, giving you a good starting point for learning more about collision systems. Drop the video a like to let me know if it was, and if you've got any questions, let me know in the comments below. Thanks for watching, and goodbye.